Day's Explainer. I am absolutely thrilled to guide you through this one, mostly because we're looking at something that feels incredibly human. We're going to master an algorithm that mathematically proves an old saying, you are known by the company you keep. We're talking about the KNearestNeighbors algorithm, or KNN for short. If you're building your understanding of machine learning from zero, you are in the exact right place. I promise you, by the end of this explainer, you're going to see just how brilliantly simple this concept really is.
Think about this for a second. Imagine you're moving to a brand new city. How do you figure out exactly what neighborhood you belong in? Well, you'd usually look around at the people closest to you, your literal neighbors. If the majority of the folks on your street love tending to quiet gardens, you're probably in a quiet, relaxed neighborhood. But if they're all staying out late and hosting rooftop parties, you're in a vibrant, bustling area. You figure out where you fit in just by looking at the people closest to you. And honestly, that is exactly the pure similarity logic behind KNearestNeighbors. There's no complex math required to understand the core idea here.
So, here's our roadmap for today. We'll start with a welcome to the neighborhood. We'll see how the algorithm actually works, look at how we measure the distance between points, build and tweak some models, and finally, explore some real-world uses. Think of this as a fun, logical tour, rather than some daunting technical syllabus.
Okay, welcome to the neighborhood. Let's just dive right in and define what KNN actually is.
Okay, I know that definition looks like a massive mouthful of technical jargon, but let's translate it, because it is wonderfully straightforward. KNN is a machine learning algorithm used to predict outcomes. It's called non-parametric. That is literally just a fancy way of saying it makes absolutely zero assumptions about your data. It doesn't assume your data forms a nice bell curve or a straight line, it just takes the data exactly as it is. It's also called instance-based, and this simply means instead of learning an abstract mathematical model, it has a perfect memory. It literally memorizes the entire data set. To make a prediction, it just looks at the k nearest points, k being whatever number of neighbors you choose to look at.
So how does this algorithm actually work in practice?
Let's take a look under the hood. The whole thing runs on just 4 basic steps, entirely without complex math. Step 1, store all the data. Remember, training in KNN is just remembering. It literally just saves the data to its memory. Step 2, when a new point comes along, calculate the distance between that new point and every single point you have stored. Step 3, find the k points with the shortest distances. Those are your nearest neighbors. And step 4, take a vote. If you're doing classification, it's just a simple majority vote. It's exactly like asking your 3 closest friends what to eat for dinner. If 2 say pizza and 1 says sushi, guess what? You're having pizza. If you're doing regression where you're predicting a number, you just take the average of what your neighbors say. Super simple, right?
Which brings us to measuring the distance between points. We know we need to find the closest neighbors, but how do we actually measure that physical space?
This is where it gets really visual. We basically have 2 main ways to measure distance. First is Euclidean distance. Think of this as the straight line a bird flies from point A to point B. It's the most common method and works beautifully for standard numerical data. But then we have Manhattan distance. Imagine you are in a yellow taxi in downtown Manhattan. A taxi can't just fly in a straight line through the skyscrapers, it has to drive along the grid of the city blocks. Manhattan distance measures exactly that, the grid-based path. And it turns out, driving the city blocks is actually way better when you have highly complex, high-dimensional data, because it's much less sensitive to crazy outliers.
But we don't just stop at birds and taxis. We've got different measuring tapes depending entirely on the type of data we're looking at. For example, the Minkowski distance is actually a master formula. It can act like either Euclidean or Manhattan depending on a single parameter you give it. And then the Hamming distance, well, that's a special measuring tape used specifically for categorical data or text strings. Kind of like comparing 2 words to see exactly how many letters are different. The big takeaway? Ensuring we always use a meaningful distance metric for our specific data type is absolutely key to making KNN work.
All right, let's move on to building and tweaking models. We get the logic, but what does the code actually look like?
I love this because it brilliantly illustrates just how accessible machine learning can be. If you're using Python and a library called scikit-learn, building this algorithm literally takes 3 lines of core code. You build the model and tell it how many neighbors to look at, in this case 3. You store the data using model.fit, and you make your prediction using model.predict. And that's it. You've gone from absolute zero to a functioning machine learning model in just 3 lines. Amazing.
But of course, there is a catch. You have to choose your k value, that n_neighbors hyperparameter we just saw in the code. And this is hands down the most important decision you'll make.
If you pick a k that's too small, like k equals 1, your model becomes incredibly sensitive. It's going to overreact to every single noisy data point. It's kind of like judging an entire neighborhood based on just one loud neighbor. But on the flip side, if you make k too large, you smooth things out way too much and dilute your local community, completely missing the distinct local patterns. You really have to find that Goldilocks number of neighbors.
And this brings us to the rules of the neighborhood. Now, while KNN doesn't assume much, it does make a few demands. It assumes similar points are near each other, and the noise is limited. But the most crucial rule? Your data absolutely must be properly scaled. KNN is highly sensitive to feature scale. Think about it. If you're comparing a person's age, which goes from 0 to 100, with their income, which might go from 0 to 100,000, the income will completely dominate the distance calculation. You have to scale or normalize your data first so everyone is playing on a level field. Do not forget that step.
So let's look at some real-world applications. Where do massive companies actually use this logic?
First, let's talk about why they love it. What's really interesting here is that second point, no training phase required. Because KNN simply memorizes the data, it is instantly ready to use the very moment you store the data. There is no waiting around for hours while a computer crunches some abstract mathematical model. It's incredibly simple, it naturally handles weird nonlinear data boundaries, and it can effortlessly tackle problems where there are tons of different categories to choose from.
But to be fair, we have to balance the scales. Having a perfect memory comes with a heavy cost. Because it has to calculate the distance to every single training point to make just one single prediction, it is incredibly slow when you actually ask it for an answer. It's also a total memory hog, because it has to keep the entire dataset loaded up. If you try to use KNN on a massive million-row dataset with a bunch of irrelevant features, its performance is going to drop right off a cliff. It is brilliant for small to medium datasets, but it definitely struggles under massive weight.
Yet despite those limits, this thing is everywhere. Think about how you use Netflix or Amazon. When Netflix recommends a movie to you, a massive chunk of that logic is based entirely on finding users who are in your neighborhood, users who watch and rate things similarly to you. If your 5 nearest neighbors loved a movie, the algorithm predicts you're gonna love it too. It's also used in medical diagnosis to find similar historical patient cases, in handwriting detection by comparing the pixel shapes of letters, and in segmenting customers into groups. It is literally similarity in action.
So, KNearestNeighbors is beautifully simple. No complex math, no long training phase, just the completely logical idea that nearby points are similar. But what happens when we need something that doesn't struggle with large datasets? What happens when we want the absolute cutting edge? Well, in part 9 of our series, we're going to explore gradient boosting, the heavy-hitting algorithm that literally wins machine learning competitions by building models sequentially, with each new model learning to correct the errors of the previous one. It's a game changer, and you'll not want to miss it, so make sure you join us for that explainer. Until then, stay curious, and I'll see you next time.